I'm Professor Rad, and this is Precalc video 230, Applications of Exponential and Logarithmic Functions, Finance. So today we're going to be talking about different applications exponential functions have for financial purposes, primarily in calculating interest. So we have three formulas over here on the side. So there are three types of interest that we're going to be talking about. So we have simple interest, compounded interest, and continuously compounded interest. So essentially what this means is, let's say you take out a loan for, I don't know, for 5 months. So what simple interest will do is it will take the amount that you borrowed, and at the end of the 5 months, it'll take that amount you borrowed, which is called the principal, and add the interest onto that. So the interest is an extra amount that you pay for a given, percentage of the amount you borrowed. For compounded interest, what that means is that instead of the interest being calculated at the end of the loan period, so in this case, the 5 months, they're going to say, if they compound every month, they're going to say, here's how much money you had at the end of the month. Let's figure out the interest then. Then how much do you owe at the end of 2 months? Now we'll add more interest onto that. And so your interest is recalculated multiple times. And so you have a little bit of interest being added on at regular intervals. So ultimately, this tends to make you have to pay more long-term for your interest. So for the lending agencies, this is great, right? Because if you compound interest more often, you can be getting more money from the loan. So sometimes interest will be compounded monthly, sometimes daily, sometimes weekly. But from the lender's point of view, it's great to have interest compounded as often as possible, because now you're compounding more and more and more interest, so you're gaining more money. So that's what continuously compounded interest is. And I ran out of room that says interest, but it's very tiny at the end. So continuously compounded interest is if you're getting that interest added on continuously. Instead of every month or every week or every day, it's continuously, every fraction of a millisecond and then some. So these are our formulas, and these are the variables that are used in them. So for our simple interest formula, each of these you'll notice has A of t. So you can think of A of t as function notation, the amount at time t. So A of t is called the future value, because that's how much money you will either have accrued in, say, a savings account, or how much you will owe if it's a loan at time t. For simple interest, you're going to take the principal and multiply it by 1 plus your interest rate times time. So typically interest rate will be given to you as a percentage. So when we go to substitute into the formula, you want to change that percentage into a decimal format before you go ahead and find the calculated value. Then for compounded interest, a similar pieces, we have principal, P, R, rate, and T, time, but we need to make sure that we're incorporating how many times we're going to be compounding. So this K value that you see is how many times we compound per year. So if I compound monthly, K is going to be 12, because there are 12 months in a year. And if K is daily, it would be 365, and so on. And then for continuously compounded interest, we notice that we have a natural exponential function showing up here. So this is one of those places where E shows up pretty naturally. And we can see it kind of happening because E is defined to be 1 over n, or 1 plus 1 over n to the nth power as n goes to infinity. So if I look at my compounded interest formula, think of R as like 1 for just a minute. So we would have 1 plus 1 over k to the k power, all that being raised to the t power. But this would end up being just your E value. So as k goes to infinity. So that formula that's used to derive E is cooked up in this formula here. So that's essentially, that's not the formal proof of why it's there, but it kind of is the evidence that's laying the foundation. So for our continuously compounded interest, I think of this as the PERT formula, because it's P times E to the RT. All right, so these are our formulas. So let's go ahead and apply them in 4 examples. So basically, we're going to look at one scenario where you deposit $880 in an account, and it has an interest rate of 0.5% annually. And we want to know how long it's going to take us to have $1,000 in the account. So, $120 extra. If the interest is simple, compounded 24 times each year, compounded every other month, and compounded continuously. So let's go ahead and work through this. So for before I use any of this, actually, over here on the left, I'm going to summarize the information given to us. So we deposited $880 in the account. So the amount we had deposited, or the amount you borrow in these situations, is going to be your principal. So that's P. P is going to be $880. It says interest is earned at a rate of 0.5% annually. So R is going to be 0.5%, which is the same as 0.005. So we want R to be in decimal form when we go to use it in the formulas. So I like to find that here. Then it says, how long will it take you? So it's asking us how long. That means it's asking us for time T. So T is what we're looking for. So how long will it take for you to have $1,000 in the account? So $1,000 is the amount we want to have in the future. So they're telling us A of T. So A of T is equal to $1,000. And then we have different ways that that interest is being computed. Now, I'll also point out here that in this particular problem, each of these instances, we're going to be solving for time. So we're going to be solving for T, but that won't always be the case. Sometimes I'll say you have a principal of 880, the interest rate is 0.5%. How much money will you have in the account after 5 years? So in that case, I would have given you time and you'd have to find the future value. So this summary is helpful because it not only, helps you to summarize the information that you have, but it also helps you to know what information you're looking for and how to apply this information into those formulas. So let's go ahead now and we'll solve each of these. So let's keep that off on the side there. And for part A, it says the interest is simple. So because the interest is going to be simple, we're going to use the simple interest formula. So I'm going to go ahead and write that on the side. So A of T is equal to P times 1 plus RT. Next, we're going to substitute in the values that we have. Remember, A of T is our function notation. So this doesn't mean the future value times T. It means the future value at times T. Okay, so this is like saying f of x equals whatever. So for A of T, we're going to substitute in this future value of $1,000 that we wish to have. The principal we're starting out with is 880. Our interest rate is 5, what is that, thousandths? So 0.005. And T is what we're looking for. So we're going to leave that at T there. So now we have a linear equation to solve. It's linear because T is just a T. It's not like e to the T or T squared. So if we wish, we can distribute that 880. Let's go ahead and do that. And we'll need to do 880 times 0.005. That'll give me 4.4. Next, we'll subtract 880 from both sides. And that gives me 120 on the left. And if I divide by 4.4, I'm going to get 27.27 repeating. So I did kind of squish in here, very small, to the nearest year. So to the nearest year, this is going to be 27 years. So I'm going to put that over here on the side, 27 years. This is a long time for our savings to grow by just 120 bucks, right? So this is a long time to wait for that money to accrue. So with simple interest, it tends to grow pretty slowly. Our interest rate here as well, the 0.5% is really small. So in all of these cases, the money is not going to be growing very fast. So let's take a look at part B. Part B, C, and D, they all involve compounded interest. So part B says we're going to be compounded 24 times annually. So that information they're telling us is our value for K. K is the number of times the interest is compounded annually. So here we're compounded to 24 times annually. That's telling us that K is going to be 24. We need a value for K because in our compounded interest formula, it looks a little bit different from our simple interest, right? So I'm going to substitute in pretty much all the same values, and now I have to include this value of K. So let's go ahead and do that. So I'm going to rewrite my formula. A of t is P times 1 plus R over K to the KT power. So A of t is 1,000, just like it was before. P is 880, just like it was before. 1 plus, and now instead of R times T, I'm going to have R over K, so 0.005 over K, which was 24, to the KT power. So this is 24T. Now we have some not so great news. The not so great news is that this is no longer a linear kind of equation. In this instance, this is going to be an exponential equation because the variable is in the exponent. So we're going to have to use a logarithm in order to solve this. What I propose we do is start by dividing both sides by that 880. This will give us this number to the 24t power. So let's do that first. Let's divide both sides by 880. And we get 1.1 and then repeating 36s. So I'm going to change that into a fraction and get 25 22nds. So when I divide both sides by 880, I get 25 over 22 is equal to 1 plus, let's see if we can simplify this a little bit. 0.005 divided by 24 is kind of a gross decimal. Let's see if we can convert that to a fraction easily. Not so nice. So this is not going to give us a fraction super nicely. So I'm just going to leave it in this format because I want my answer to be as precise as possible at the end. If I start rounding values now, especially because this is exponential, that's going to cause a lot of round off error at the end. So it's kind of a pain that we can't really simplify this to look really nice at the moment, but you know what, that's okay. We'll work with it. Whew, okay. Now we can use any one of our techniques to go ahead and solve this. What I'm going to do is I'm going to use the natural log. So I'm going to take the natural log of both sides. If you want to take log base, whatever the heck this number is, you can do that as well. It's really up to you. But I'm going to use the natural log of 25 over 22. And that's going to equal the natural log of 1 plus 0.005 over 24 raised to the 24t. Now, the reason I'm choosing to use the natural log here is because my calculator only does common log and natural log. So if your calculator easily does a logarithm with any base, then it would probably be easier to actually use this as your base. But the reason any logarithm is going to work is because we have that property that says if you have a log of something to a power, you can bring that power out front as a factor. So what this is going to do is it's going to take this exponent of 24t and bring it down to the land of the living, right? It's going to bring it down so that it's a coefficient of this logarithm here. So we get the natural log of 25 over 22 is equal to 24t times the natural log of 1 plus 0.005 over 24. And so to get t by itself, I'm going to divide both sides by the product of 24 and the natural log of this expression. So we're going to get a really gross looking expression here, the natural log of 25 over 22 all over, and we're dividing by 24 times the natural log of 1 plus 0.005 over 24, and that's going to equal t. Now, if I was going for an exact answer approach, I probably would do a little bit more work to write this expression as a fraction instead of as just this mess. But because we're going to be rounding to the nearest year, I want to keep things as precise as possible, but not do more work than I need to do. So I'm going to keep it in this format and then just throw that into my calculator. So I've got to be careful about my parentheses, but as long as I'm careful about my parentheses, I should be okay. So I've got the natural log of 25 over 22, and I'm going to divide that by 24 times the natural log of 1 plus 0.005 over 24. So we've got, I think all my parentheses are in place. And this is going to give me 25.569 approximately is equal to t. And so to the nearest year, we're going to get 26 years. Hey, look at that. If we compound 24 times a year, so twice a month, we get to shave a year off in our savings of $120. Woo! So take a moment and see if you can work through part C on your own. And then I'm going to erase this and I'm going to work through part C and we'll see what we get. So pause here. I'm going to pause here and work through it. So you pause and work through as well. Alrighty, so how did we do? So I got 26 years. So the same thing we got in part B when we rounded to the nearest year. I think it was off by like a 10th or 100th of a year. I think it, yeah, because here we have 0.57 and I think the other one we had 0.569, something like that. So here's how I walked through it. So for part C, it says we're compounded every other month. So because there are 12 months in a year, if I compound every other month, that means I'm compounding just 6 times in the year. So in part B, we compounded more often, 24 times a year. In part C, we're only compounding 6 times a year. Then I substituted into the formula, and really the only difference here is that I have a 6 in the denominator and a 6 in the exponent, whereas in part B, we had a 24 in that spot. Now this time I did decide to go through the work and figure out what the fraction was. So the fraction works out to be 1201 over 1200. And then I just used the same steps to solve as before and evaluated this mess and got 25.577, which to the nearest year is going to round to be 26. So we can see whether we compounded 24 times annually or 6 times annually didn't really make a big difference in our result here. But what if we were to compound infinitely many times per month? So if we were to compound continuously. So let's take a look at that one. So for part D, if I'm going to be compounding interest continuously, that means I'm going to be using the continuous compounded interest formula, which was our third one listed over here. This is the one that spells out PERT, right? So we have the principal times e raised to the RT power. So I'm going to substitute in same values as before. Notice for continuous interest, we no longer have that K in our formula. That's because the E kind of comes from the origin of K going to infinity. So we're going to have $1,000 is equal to 880 e to the 0.005 t. Now to solve this equation, we're going to begin as we did last time and divide both sides by 880. That's going to give us this exponential expression all by itself. So just like before, we're going to get 25 over 22. And that equals e to the 0.005 t. Now this time we can also take any logarithm of both sides. So we could take the natural log of both sides. But because e is the base of the natural log, I'm just going to write this exponential equation as a logarithmic equation. So remember, we have log base e of this value is equal to the exponent. So log base e is the natural log of this value, 25 over 22, is equal to our exponent. Then we'll just divide both sides by 5,000, and that will give us our value for t. Again, because we're looking for an approximate answer here, I'm not going to be super careful about simplifying this expression. I just need to evaluate it to the nearest whole value. So we have the natural log of 25 20seconds, and we're going to divide that by 0.005. So this is going to give me 25.567 approximately, which to the nearest year is going to be 26. So in this particular situation, what's going on is our interest rate is so low, that 0.5%, that doesn't really matter how frequently we compound. It's still going to take us 26 years to earn that 120 bucks. So savings accounts tend to have very low interest rates. So you don't really get a lot of money from a savings account, unfortunately. Meanwhile, loans tend to have higher interest rates because, you know, that's how banks make their money. So. All right, so that's going to be it for this video on financial applications of exponential and logarithmic functions. In this video, we primarily had exponential functions for compounded interest, either for a particular interval or for continuously compounded. So we tended to have exponential equations, and then we needed logarithms to solve those equations. So that's also going to be the case in our next couple of videos. And what I want you to pay careful attention to is, see this compounded interest formula, P times E to the RT. See if the formulas in the next two videos look anything similar to that. So that's all we have for this video right now. I hope you found it interesting in computing interest. And yeah, I look forward to seeing you in the next one. Bye for now.